welcome to this morning session. And it is my pleasure to introduce Leonardo Mihalcea, who's going to talk about mother classes for Grassmannians and Schubert varieties.
Yes.
Yeah, Schubert.
Grassmannians, thank you very much. Yes. At the end of the talk, I'm going to switch to slides, so maybe I'll give a sign. Okay, so first of all, thank you for the invitation. It's a pleasure to be at the conference. It's an honor to actually get to speak. So it's a great place to be. I'm going to talk about something that was discussed already in this conference, namely about mother classes. Later on, you're going to see oil abstractions will come up in this talk. Maybe what was discussed a little bit less was this Grassmannian situation. So I'm going to discuss about mother classes for the Schubert varieties in Grassmannians. And I put here a list of people. So this particular work, which is available on arXiv, is already published. It was with my former postdoc, Singh. But there were some other people that calculated mother classes for Schubert varieties in Grassmannians. It depends on how you take things, but I was a bit loose on the literature here, so you can extract information, concrete calculations about mother classes. For example, from the work of Ressler, Finkelberg, and Lutz, they actually proved, so their work has to do with geometric representation theory. They proved that the IC complex of a Schubert variety in Grassmannian is irreducible. And then if you have such an information, you can obtain a particular algorithm to calculate mother classes for Grassmannians. Then Bo and Fu looked at the reducibility of the IC sheaf. I'll explain a bit later on, but for other Lie types, so for classical types A to D. Benjamin Jones actually calculated both the CSM classes for Schubert cells and also the mother classes. Shipping has similar formulas, but for determinantal varieties, which could be thought in some cases some special type of Grassmannian Schubert varieties. And finally, Richmond, Slotstein, Wu, they actually calculated the Nash blow-up of the Schubert variety. And their work is in fact contemporaneous with our work. And the things that you're going to see in this talk are in some sense very much related to what they do. So let me start with the basic definitions. So I have a peculiar way to calculate mother classes. So it's not the most standard way, which starts with the definition of Nash blow-up and so on. So this way of computing uses conormal cycles. So this definition comes from the work of Ginsburg and Sabah, which has this Lagrangian point of view on constructing characteristic classes. So you start with the following situation. So you have y in x, where x is smooth, and then y is so this is a closed variety, and y is irreducible. And then you construct this conormal cycle, which is by definition the following thing. So you take the conormal bundle over the regular part of y inside x. So this is going to be a Lagrangian. Well, there's going to be a locally closed Lagrangian cycle inside the cotangent bundle of x, and you close it up.
Why?
Why?
No, it means you
No, I really mean that.
You put x.
Oh, of why you put it in the index.
Yes.
Yeah, that's fine.
So this is that. Okay. So this is what I'm gonna call by definition. This is gonna be this conormal cycle. This is d star y x. Yeah. So y is it here? So this is the closure of the conormal bundle of the regular locus in of x of y regular in x, and then the closure is taken inside the cotangent. So this is now a closed Lagrangian cycle inside the cotangent bundle. And then I want to give the definition. So using this, I'm going to give the definition of the mother class. And again, this definition really comes, I think Ginsburg was 86 and maybe Sabah was 85. So I'll say it this way. It comes from this perspective of constructing characteristic cycles using Lagrangian cycles inside the cotangent bundle. So you say that the mother class of x. Let me put this in a picture. So we have this. We have this. We have the projection phi. Okay.
Then you also have the zero section. So this is the zero section. Okay. And then you say that the mother class of Y is by definition, there's a sign, which is annoying, but it has to be there, as you'll see in a moment. And then you pull back this thing. Okay. And what I just wrote is wrong. Because if you just do this naively, right, so what are we doing here? So we're pulling back a Lagrangian cycle from T star of X. So this is middle dimension. So being middle dimension, this means that it's going to live inside here, right? But inside here, there aren't too many classes here. Okay, there are very few classes. So what you want to do is, in fact, you want to put a C star action here.
If you would do it without the C star, it would be the degree zero mass.
Yes, but I want the full mother
Yeah,
class.
clear.
Yes. So, so what I want to do is I want to put a C star action on the cotangent bundle, which acts by dilation on the fiber, and for technical reasons, I want the character to be H inverse, or additively written is minus H, so this acts there. So then I want to take this pullback in a C star equivariant way. And then the whole thing is going to live in the C star equivariant.
Then you need the zero. Oh, no, it's still fine.
It's still fine. So this is, so the point of this is that what is this saying? So this is, so what is a class here? So a class here, it's a C star equivariant class of degree 0. Now, what are such classes? So such classes can be written as A0 plus A1H plus A2H squared plus right? So in other words, you want to put these powers of H so that everything at the end is in degree 0. So if AI is in A lower I of X, then if you put AI H upper I, it's going to be in A0 C star, right? Because you have a homology class capped with a cohomology class of the same degree, so you're going to end up in degree 0. So this is in some sense what this is doing. This is homogenizing a non-homogeneous class. Okay, so this is just homogenizing a non-homogeneous class, and if you want to kind of switch between the two worlds, you either dehomogenize or homogenize. So if you want to see the non-homogeneous class, then you make H is equal to 1. Or if you want to see the homogeneous class, then you just take a non-homogeneous class and you put appropriate powers of H. You can only put it in a single way. So that is the definition, and I'll try to convince you. Let me give you an example. I'll try to convince you that at least in the classical example that you know, this actually coincides with what you expect. So, so if we take y equals to x, then what do we have here? So let's calculate. So this is minus 1 to the dimension of x times the pullback T star xx, okay? But done in this C star equivariant way. Okay? So this is T star xx is just the zero section. So now I'm pulling back the zero section. So this is the self-intersection formula. If you pull back the zero section, you get minus 1 to the dimension of x. We know from intersection theory, this is going to be the C star equivariant top Chern class of the normal bundle of the zero section. So you have to take the C star equivariant top Chern class. The top Chern class here is the dimension of x, and then what is the normal bundle? Well, the normal bundle is T star. Right? This is the normal bundle of the zero section inside the cotangent bundle. Let's calculate this. So remember that the character that we chose is minus H. So how do you calculate a top Chern class? If you know the Chern roots of the bundle, you just multiply the Chern roots. So what you get here, it's minus 1 to the dimension of x. The Chern roots, remember that this character minus H actually acts on the fibers of this cotangent bundle. So in fact, the weights of the normal bundle will include this minus H. So there will be minus H minus x1, minus H minus x2, minus H minus xn. So what are these x's? So the xi's are the Chern roots of the tangent bundle. So these are the Chern roots of T of x, of Tx, right? So So because xi is the chain root of t of x, then minus x is the chain root of t star. Okay. But because I'm going in this normal direction, I also have this contribution coming from the c star action. So I have this. So of course I have minus 1 to the dimension of x. That enters into that calculation. So I get really h plus x1 dot 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 h plus xn. Okay. So this is the homogenized version of the mother class. Now I want to dehomogenize. So if I want to take h equals to 1, that means dehomogenize the class. Then what you get is just 1 plus x1, 1 plus xn, which of course is just the total chain class of tx. So what did we prove here? We proved that the mother class of x is equal to the total chain class of tx, which is what you want.
And your calculation shows why you have to use the character minus h and the minus in front, because everything is in terms of t cotangent, but you want to fit with the normalization with the tangent.
I mean, I could do h equals minus.
Yeah.
Yeah.
Can put it.
It's nice to have minus h. Yes.
But maybe you should give the hint that the description you give is not the original description of Sabagin.
So this is not the original description of Sabagin. Good job. That's my hint. Yeah, so okay. So how does this help? So fortunately, if you look in intersection theory, there are formulas to calculate pullbacks via the zero section. These formulas for the pullbacks via the zero section can be calculated essentially in terms of Segre classes of cones. So I'll remind you now what the formula is, and we'll see what we do with it. So I'm still in the general situation, so this is very general. Everything works in general. Okay, so I'll erase maybe this example. So a fact which you can read in, I think maybe section 3.3 in Fulton's intersection theory, something like that. Okay, so you have, if you want to pull back this class, in fact, you can pull back any cone, it doesn't really matter. So let's just pull back a cone. So this is going to be, and I want to pull it back C star equivariantly with some character chi. Then this is going to be just the total chain class of the tangent bundle intersected with the Segre class of the cone C. So C here is the analog of this Lagrangian cycle, right? This is a cone inside the cotangent bundle. And then I have to homogenize with respect to the character chi. Okay? So that is a fact. Why is this the case? I mean, this is the case because if you look again, this is something very general. So if you have something like the cone is, you have a cone in a vector bundle over X, and then you take the projective completion, and then you have a diagram like this, and then you have this I here. Then it's a fact that if you want to pull back C, then what you get is this. So it's the pullback of it's essentially related to the Segre class. It's the pullback of the top chain class of Q here intersected with C bar. So Q here, so you have something like this, O E of minus 1. And this is E plus 1. And this is Q, which is there. And this is closely related to the definition of the Segre classes. Let me also remind you what is the definition of the Segre class. The Segre class, by definition, is kind of the same type of thing. You just have the class of C bar here, and on the bottom here you have the total chain class of OE of 1, of E of minus 1, sorry, of E of minus 1. Okay. So in other words, this is going to be something like this. So you take a sum, you take C of O1s, OE of 1s to the I, and then you can't. So this is close, so from the Whitney sequence, the top chain class of Q is closely related by dividing by this O E of -1. So you play with that.
Maybe you should hint that Fulton chapter 3 does not do this.
So Fulton chapter 3 does not do this equivalent. Huh?
You can dehomogenize. So that
You can dehomogenize. So yes, I mean, people are saying the right things, which are, and I'm, indeed, these type of things are not exactly written in the way they are written. I mean, if you look in Ginsburg or Saba, you will not exactly see this type of thing. If you look in Fulton, he certainly doesn't do things system equivalently. But the main ideas are there. Some kind of, I think I'm giving the right credit to.
this formula is even in the introduction.
Yeah, and this is a basic formula. Okay, so why do I want to do this? Okay, I want to do this because it turns out that Segre classes are very nice objects. In particular, these Segre classes satisfy two important things that we will use.
Maybe, Max, this is exactly what Lorenzo was using in his talk, what he called his Chern class of a code.
That is correct. That is correct. So
Exactly
Laurentio, that is correct. So Laurentio was, he was using the pullbacks, but yeah, essentially, this picture and Laurentius picture are completely equivalent. They can be written one in terms of the other. Yes, this is, yeah. So I want to say two facts about Segre classes. So two nice facts. So if C is a bundle, so this is a vector bundle, then the Segre class of a vector bundle is just 1 over the total chain class. So we know how to calculate Segre classes in the situation when the cones are vector bundles. And the second thing that I want to say, and this is in fact a key fact, which is, okay, so you have now a cone over some variety. Maybe this cone is included in some bundle. And then let's say you have a situation like this. So you have a proper map here, and you have something like C prime here. And let's say that this is proper and birational on top here. Okay? So you have some situation where this is, so you have a proper map, and you have a birational map from one cone to some other cone. Then what happens is that the push forward of the Segre class is the Segre class. Okay? So why is this important? This is important in case you somehow know how to desingularize your cone by a vector bundle. If you know how to desingularize a cone by a vector bundle, then it's easy to calculate Segre classes of vector bundles, and then you just push forward. So that's the strategy that we're going to follow here. So the strategy I'm going to follow for these Grassmannian Schubert varieties is that I'm going to have this conormal cycle for a Grassmannian Schubert variety inside the cotangent bundle of the Grassmannian. And then it turns out that we can actually write down a resolution of singularities of that. And the reason we can write out a resolution of singularities for that is because of Lie theory, essentially. There's some kind of miracle that happens, which I will explain.
That is where the origin that you got for Grassmannian is coming.
Yeah. So this is where the Grassmannian comes up. So the Grassmannian sounds like a very strong restriction, and unfortunately, I don't know what to do beyond Grassmannians. And you'll also see why. So, but I'll tell you what happens. Okay, so that's gonna be the strategy, right? So I'm gonna use this formula. So this formula tells me that what I'm interested in, which is this mother class, it's essentially a pullback by the zero section of the conormal cycle. This pullback can be interpreted, can be calculated in terms of the total chain class, which you always know. This thing you always know, and the Segre class of the conormal cycle. And the way I will calculate this Segre class is by desingularizing, by finding some desingularization, so using this type of diagram here. So finding some desingularization and then pushing forward.
You don't require X prime to be smooth, right?
I don't require X prime to be smooth, no. In fact, this is, so this is, actually this is honestly, well, in fact, not even this one, Fulton doesn't write it quite like this.
So it's horizontally singular.
Yeah.
So it comes up in Tom polynomial theory. So it's horizontally singular, vertically smooth.
Yes. Yeah, so, if you really insist on everything to be smooth, you can, of course, desingularize this. But this is like overkill.
Yeah, I don't want it.
It's like, you can kind of like by Hironaka, you can find a resolution of singularities here, and then you can just pull back this bundle here, and everything is going to be completely smooth. But why do
No, why? It's just a push forward map has to be a more
Yeah,
complicated denominator.
yeah, that's right. That's the only thing you need. So in this case, this x prime, so x will be for me a Schubert variety. X prime is going to be again a Schubert variety. In particular, it's not going to be smooth. You can think of it as a Nash blowout.
Yeah,
we'll see.
I see that.
But and then we're going to have a bundle over this Nash blowout, which we'll be able to calculate the second class of that bundle, and then we'll push that forward. That's the formula at the end.
But it seems to be that this construction exists for.
This construction exists, but if I give you like a particular cycle, then
Okay.
yes, yeah. In general, everything exists here. It's not yes, but in practice,
What I mean is not only for Grassmannian, but partial regularity.
this reminds me of a quote. It says
From
that-
Heidegger.
Not Heidegger. Yeah. In theory, there is no difference between theory and practice, but in practice, there is.
It's probably more knows, right?
So it's like this is one of these things. Anyway, so let's just do this, okay? So that's the strategy. So you've seen the strategy. Let's actually implement the strategy and see where we get. Okay, so now I have to switch to Grassmannians. Let me see if I wanted to say anything else. No. So I want to switch to Grassmannians. So the goal is gonna be. So I'm gonna work with the complex Grassmannian, but again, for people that know, this is gonna be a cominuscule Grassmannian. So cominuscule Grassmannian. A cominuscule Grassmannian is something of the form G mod P, where P is a maximal parabolic, which corresponds to a cominuscule root. So a cominuscule root is a root which appears with coefficient 1 in the highest root of the root system. So Grassmannians are like that, Lagrangian Grassmannians are like that, maximal orthogonal Grassmannians are like that. In type E6, there's something called the Cayley plane, and in type E7, there's something called the Freudenthal variety. So I'm only doing it for Grassmannians, but the type of combinatorics I'm using can be written in that. Okay, so what do we have there? So we have Schubert varieties. So for Grassmannians, I'm going to consider this K by n minus K rectangle, and then I'm going to consider partitions in it, lambda. So what is lambda? So lambda is just a sequence of non-negative integers, which has at most K parts. And then the first part is at most n minus K. So this is going to be a Young diagram. It can be represented as a Young diagram in this record. And then for each such partition, we can define a Schubert variety, omega lambda, which is defined as subspaces of dimension K, with the property that the dimension of a V intersecting with C, and this is n minus K plus I minus lambda I larger than I. So this is just a definition of a Schubert variety. Okay. So this is an irreducible variety. There is a big open cell inside it, which is isomorphic to an affine space. And what we know is that, for example, we know that cohomology of the Grassmannian, cohomology or homology, is freely generated by fundamental classes of these Schubert varieties. So for me, if I want to say that I understand some class, well, maybe I shouldn't say I understand some. If I want to say that I can calculate some class, for me means that I should be able to take that class and expand it in this basis. This is like a God-given basis. It's given by the stratification by Borel orbits of the Grassmannians. So if I understand how to expand my class into Schubert classes, then I'll say that there is some type of computation out there. So that's going to be the goal here. The goal is going to be to take the mother class of a Schubert variety and expand it out in terms of with some a lambda mu, and expand it out in terms of the Schubert varieties, and kind of give a combinatorial algorithm to determine what is this. Okay, so what do we want to do? So now we have to start the game, right? So the diagram that we're gonna have is gonna be something like this. So we will have the Schubert variety. Over the Schubert variety, there's gonna be this cone. The Schubert variety, it turns out, is gonna be there's gonna be some other Schubert variety, but in a complete flag manifold, which I'm gonna denote by omega w lambda, and I'll tell you what this w lambda in those pictures. So this is gonna be some Schubert variety in FLN. And then over this Schubert variety, I'm gonna construct a vector bundle, EW lambda. This vector bundle will have the property that it's gonna resolve essentially the singularities of this. So there's gonna be a birational map. But the key factor is that this is going to be a vector bundle. This is not exactly smooth yet because this Schubert variety may not be smooth, but I can desingularize further the Schubert variety, for example, by Bose-Samuelson resolution, and then pull back this vector bundle and everything is smooth. But I don't need that. So how do I construct this bundle? So this is why I made these pictures. So now these pictures actually tell you what you need to know, kind of. Like how you construct this bundle and how you see these tangent spaces, at least how you see the tangent space at the central point of the Schubert variety. So this Schubert variety always has a central point, which I'm going to denote by E lambda, which is the point where the Schubert variety is smooth. It corresponds to the big open Schubert cell inside. Okay, so it has the property that the Schubert variety is going to contain the Schubert cell, and then E lambda. This E lambda is the unique T-fixed point inside that Schubert cell. So this is a. Oh, I think with the notations that I just gave you, probably everything that I'm going to say is it's opposite, but I'll ignore that. I guess I'm recorded, so maybe I shouldn't just ignore it. So this is going to be K and minus K. There's always this annoying fact that I have to choose the right conventions to make things fit with the dimension or with the dimension. Okay, so I want to use the following conventions, which I think they're not going to fit exactly this definition, but you'll see this on this board. So let's say that let's say that we work in GR3 cell. And let's say, okay, do you have any favorite partition here, which is not too easy? In 2-1. Let's take 3-1. 2-1 is too symmetric. Okay, so 3-1. So 3-1 goes like this. Right, so this is 3-1. So I have 3 boxes here and 1 box here. Also 3-1 goes like this. Okay. So first of all, because you gave me the partition 3-1, I'm going to be able to do 2 things. First, I will give a reduced decomposition for the Val group element which corresponds to this partition. That reduced decomposition is obtained in the following way. I look at these boxes, and I only look at the boxes which are inside my partition, and I read the boxes bottom to top and right to left. The way you remember is that you always have to end up with this S3 if you want to be a minimal representative. So in this case, W lambda is going to be S2, so bottom to top, S2, and then S5, S4, S3. Okay. So this is what the first picture is giving you. The first picture is giving you a reduced decomposition. The second picture is giving you the set of roots which are sent to negative roots under this W lambda. So let me just rewrite here. So alpha, you take the set of roots, positive roots, with the property that W lambda of alpha is less than 0. So you take the set of roots which are sent to negative roots under this W lambda. How do you read those? Are exactly those enclosed by these things. So in this case, it's just this E3 minus E4, which is the simple root in this case. So this is E3 minus E4, E3 minus E5, E3 minus E6, E2 minus E4. You may ask, what does it have to do with geometry? Well, we work in a homogeneous space, and we know how to calculate tangent spaces in homogeneous spaces. So the homogeneous space that we're working in is the Grassmannian of 3 planes in C7. And this can be written as SL7 divided by P3. So this is the parabolic that is obtained in the following way. Okay, now it's going to be part 2. So I'm going to have to put a 3. Okay, so it's going to be something like this. This is going to be 3 and 4. And these are going to be the roots here. So the actual parabolic is like things here. Okay, and these are going to be 0. This is the parabolic. This is the, okay.
The first is 3.
Huh?
The first should be square. 3, 3.
The first should be square 3, 3. Yes. Yes. So this is going to be 4, and that's going to be 3. Thank you. Thank you. Thank you. Okay. So then we know from Lie theory that if you want to calculate the tangent bundle at the identity on GR37, it's going to be what? It's going to be the Lie algebra of SL7 divided by the Lie algebra of P3. Right? This is from Lie theory, because we know how tangent bundles to groups are. Now, of course, we're interested in the cotangent bundle, so I'm going to take the duals of everything. The Lie algebra of P contains all the positive roots and some negative roots. If you take the duals, then you only have positive roots in those. If you write down what those positive roots are exactly these roots here. So the roots that I wrote here are exactly the cotangent bundle at the identity on the Grassmannian. And what do I mean? In what sense a space is a bunch of roots? The space is a vector space, right? But this is not just a vector space. It's a vector space of the correct dimension. So you can see here the dimension of GR37 is 3 times 4 is 12. I have 12 roots here. But it's also a T module. So it comes with the structure of an action of the torus. And as the T module is going to split into one-dimensional T modules. So what I'm describing here are the weights of the one-dimensional T modules. So in fact, this is the cotangent space of the identity is precisely the sum of the one-dimensional spaces where you have exactly one space of each of these weights. I'm just describing what the weights are. Okay, but where is the information of lambda enters? Where is that entering into this picture? What's the geometry about? What are these roots saying here? For example, those that enclose lambda and those that are outside lambda. So it turns out that the roots enclosed by lambda correspond essentially to the roots of the cotangent space at that fixed point, E lambda, but translated to the identity so that you see inside everything inside the cotangent space of the identity. And the roots which are outside correspond to those of the conormal space, translated to the identity. So let me just write that down. So what I'm trying to convince you that although this is combinatorial, this is also geometric. You can read off geometry from this type of thing. That's what I'm trying to say. Okay, so what did I say? I said that if you take so essentially I lambda, right? So I lambda corresponds to those roots which are sent to 0. So this corresponds to this part of the picture, the part which is enclosed by lambda. So this one corresponds to the W lambda translate of the cotangent space at E lambda of omega lambda. Okay. So therefore the complement of I lambda so this one corresponds to W lambda inverse of the conormal space at E lambda. So this is going to be the conormal space omega lambda in the Grassmannian. Okay? So we just got our hands on the conormal space here. It's only at one point, but this point happens to have a dense orbit inside the Schubert variety, namely the Schubert cell. So in fact, I got my hands on the, in some sense, of the cotangent of the conormal space on the regular locus, at least over the Schubert cell of my Schubert variety. Okay. Why is this good? This is how the Nash blow-up works, right? I mean, in the Nash blow-up, you want to close things up. And then the point is that we'll be able to close such things up. Okay. How? So where is the miracle? So here's the little miracle which comes from Lie theory. So a priori, this is just let me actually give names to this. Yeah. So let me call this guy suggestively EW lambda. Okay. Maybe this EW lambda, and then we can do something. So what is this EW lambda? Let me just rewrite it. So this is the sum over positive roots. So they're gonna be roots in so roots such that W lambda is bigger than 0, right? So these are gonna be these roots in this side of the story. Okay, and then the way you write it in Lie theory, you write G alpha. So this is the Lie algebra corresponding to the root alpha. Okay. What is this? So this is a T module. This is a T module. It's a T module by definition because it's a sum of T modules. So the miracle, and here's the little miracle, and the miracle was observed by several people. I think first time was Rahul. He did that in his thesis with Lakshmi Bai, and then but Richmond, Slofstra, and Wu also have the same construction. So the miracle is that this EW lambda is also a B module, which may not look so impressive to you, but this is what makes everything work. So what does it mean to be a B module? When you have a sum of this algebra, this one-dimensional Lie algebra, I mean this is a root subspace. When you have a sum of these root subspaces, what does it mean to act with B? Right. So if I'm going to act on some single thing here, how does the action work? Well, the Lie algebra of B. So the action is the joint action. So the Lie algebra of B is going to be the sum of G betas, where beta is just a positive root, no restrictions. And then the action goes like this. So you want to look at the pairing inside the Lie algebra world between G alpha and G beta. And then two things can happen. Either alpha plus beta is a root, and then if that's the case, you get this, or it's not a root, and you get 0. So now you're acting by a joint action on this B module, and then you're asking yourself, okay, well, let's say that I'm trying to add some arbitrary positive root to some root which is already satisfies this. Am I going to land? And again, remember, the roots are the roots on this side of the story, okay? Now, add a positive root to the roots already here. You only have two situations. Either whatever you added is not a root, leaves off the table, or what you added is already here. Because when you add the root, you always go either to the right or this way, and things are already kind of arranged in this way. So there is like a natural ordering on these roots. Okay? So because of this situation, then this is a B module. So essentially, you can see from the picture. So see from the picture. If you want to do this, so it's clear in the Grassmannian situation. If you want to do it in in this more general situation, you have to use a little bit of Lie theory, but this is totally false outside these very special cases. You don't have diagrams, you don't have this type of thing. Okay, how does this help? Again, there's some symmetry coming into play. Well, now I have a B module. Every time when I have a B module, I can construct a vector bundle. That's the point here. So this is the situation. So I'm gonna so let's see where we are. So we are here, omega lambda. We have the conormal. I'm gonna construct here the Schubert variety inside FLN, which corresponds to this W lambda. So this is gonna be, I'm gonna call this X W lambda. So this is a Schubert variety inside the full flag variety. This is the Schubert variety which corresponds to this minimal length representative corresponding to lambda. It's the one that I just calculated. Okay? And then here I'm going to define this epsilon W lambda. This is by definition just X W lambda. I want to write it in fact in this way. B W lambda B cross B E W lambda. So you may know from representation theory. So what is this? Whenever you have a space, and whenever you have a representation. So if you have a space, right? So if you have a space Y, and if you have a group G and some representation of the group G, then you can form this space here. This is something very natural in representation theory. This automatically fibers over the quotient Y by G. Okay? So that's what we have here. We have a representation of B. And this representation of B, it's this E lambda. So this is going to give us a vector bundle with this fiber. This is the fiber at the origin, and the fiber, the other fibers are just translations of this fiber as you move the group around. Okay? So this is going to be a vector bundle, and this is also birational. Why is it birational? It's birational because this was exactly the conormal space at the identity on the Grassmannian Schubert variety. And this identity has, or this E lambda, this one, I erased. But that point there actually had a dense orbit. Okay, so it's very easy to see that the conormal space on the Schubert cell coincides with the space restricted to the Schubert cell. Okay? So this is going to be a natural anisomorphism. Okay, so okay, so there are no questions. So so that's what we were setting up to achieve. Now, what is this buying us? So now we have a vector bundle, and we actually understand exactly that this vector bundle is coming from a representation, and we actually understand the way that representation splits as a sum of one-dimensional T modules. Therefore, we know its total Chern class. And let me just write the formula. So
here was working because W lambda was related to a partition? Or
no, he was. You mean Rahul?
Yes, yes.
Yeah, yeah. This works because this works because it's a cominuscule space. So what happens is that in these cominuscule spaces, you know, alpha is already bigger than the root alpha 3. And now if you add another root, so I'm saying that you can, you know, if alpha is here, if alpha is in this side, right? Add another root here. You cannot end back in this side, right? You have to end either here or outside the diagram, but outside the diagram everything counts as 0. Okay? So this works because of this poset structure on the cominuscule. So you can write Young diagrams in that situation. And
maximal parabolic?
Yeah, it has to be maximal parabolic, and it also has to be maximal parabolic corresponding to this cominuscule root. The cominuscule roots mean that alpha is larger than alpha 3, and any other root that comes up in this picture has exactly that property, that all these roots are, alpha 3 comes up with coefficients exactly 1 in all these roots. So there is no coefficient of 2 of alpha 3 in these roots. This is not true for other parabolics or in other types. So the sum condition, you can probably push this a little bit further, but like not in general. This is not gonna. This is a very strong condition. Okay, so let me just tell you what is the upshot. So what are we getting? I'm just gonna give you the formula, and you probably lost the original formula. Let me just give you the theorem. So the theorem says the following. So let's say that you have omega lambda inside the Grassmannian, and then you take this I lambda that was defined before, right? So this is alpha with the property that W lambda of alpha is less than 0. And then the statement is that the mother class of the Schubert variety in the Grassmannian is the push forward of this thing. It's gonna be the total Chern class of this bundle intersected with the Schubert variety inside W lambda. So what is this P? So usually you have FLN inside project into the Grassmannian. This is P, and here you have omega lambda, and here you have XW lambda. That's the picture here. And this is in fact also birational map. So that's the push forward that I'm considering. And this can be written a little bit better. So this can be written as the push forward. This is going to be the product of the total Chern classes is going to be 1 plus C1 of the line bundle corresponding to this minus alphas. It's going to be SLM. I'm going to write it in this way. Cross B, C minus alpha. Intersected with X, W. Okay. So that's the formula here. If you remember what I wrote a while ago, the formula that I was hunting for, it was something like this: C T star of X intersecting with the Segre class of C, and then you have to do some type of homogenization by minus H. So the Segre class of C really corresponds to these roots. Well, it's the Segre class of C is 1 over the total Chern class of the bundle corresponding to these roots, but those get multiplied by the total Chern class of the cotangent bundle, which is all the roots together. So there's going to be some simplification. You only have these ones remaining, but then because you have to homogenize by minus H, you also have to change signs of these alphas. You may ask, does this look better? For me, it looks great because I know how to calculate everything here. So I'll give you some examples. So I prepared some slides. So in particular, we can calculate, we know we have formulas on how to calculate intersections of Schubert varieties with the first Chern classes of each of these bundles. This is like a very, very nice formula. It's called the Chevalier formula, and they're very nice coefficients. So this, for me, this is a formula. It can be put on the computer, and it's going to give you an answer. Now, why am I looking at this? So I'll give you examples on the slides, but let me tell you some consequences of this calculation, which I actually find interesting. So, any questions so far on this? Okay, so let me tell you some consequences. So in fact, there are at least three interesting characteristic classes for, in general, for any flag manifold and even more generally. So the first one is the mother class that we just discussed. So using this formula, we have access to the expansion into Schubert classes. But I'm not interested now in the Schubert classes. We also have access to the expansion into the CSM classes of the Schubert cells. The coefficients that come up here, they're called local Euler obstructions. So why do we have access to that? Because there are some other ways, which I'm not talking in this talk, but the CSM classes of Schubert cells are not too bad to be calculated. So you can put everything on the computer, so you'll get access to what these coefficients are. Okay, so this is the mother class. The second thing is the Kazan-Lustig class of omega lambda. So this is the class which corresponds to the IC sheaf. From this Lagrangian point of view, this class also gives you a characteristic class. And then when you expand that characteristic class in the CSM classes by the Kazan-Lustig conjectures, this expands in terms of Kazan-Lustig polynomials. So these are the Kazan-Lustig polynomials evaluated at 1.
So this local order is computed explicitly by Ginsburg.
I don't think these are computed explicitly in any situations. Ginsburg did not.
It means you can put it on a computer.
I can
get
put on,
the output,
yeah,
get the number.
They have been, yeah, they have
Not the
been
topological
defined.
definition.
Yeah, topologically we know this.
Okay, I would like to.
Calculate them.
Yeah, but here he calculates.
I calculate. So let me just say, there is a 40-year-old conjecture here, and I think so. Okay, so the point is the following. So somehow using this Lagrangian viewpoint on characteristic classes, you actually have access of multiplicities on how you expand the IC sheaf in terms of irreducible components. So when you expand the Kazan-Lustig class,
So what is the Kazan-Lustig?
the Kazan-Lustig class, if you want, you take exactly the same definition. So you take T star x, and here you put the IC of y, okay? And then you pull back by the zero section. So that's
So I
The characteristic cycle of IC.
is the characteristic cycle, the characteristic shape in the curve of IC. So that's the Kazan-Lustig class. And then if you expand the IC sheaf in terms of the characteristic cycle of the IC sheaf has some irreducible components. It was conjectured by Lustig that this thing has to be irreducible. It's false. It's not irreducible. Then it was conjectured again that it has to be irreducible in type A, like for FLM. It's false. It's not irreducible in type A. The first counterexample was found by Kashiwara and Saito. It's happening in FL7. Then, so this was happening in 80s, mid-80s, early 90s in relation to the Kazan-Lustig conjectures and the development of D-modules and all that. And it's a widely open problem to understand, first of all, when is the characteristic cycle of the IC sheaf irreducible? And if it's not irreducible, what are the multiplicities? Well, these are the multiplicities. The multiplicities are exactly the integers that appear when you expand the Kazan-Lustig class in terms of the mother class. And this is more or less by the Ginsburg-Saba point of view. So now, if you understand the Kazan-Lustig class, we understand from a computational point of view, because we understand essentially the Hecke algebra there for flag varieties. The mother class we do not understand. It's what we would like to understand, but now we understand it for Grassmannians. So what I'm saying here is that the characteristic cycle of the IC sheaf of the Schubert variety is irreducible if and only if the mother class is equal to the Kazan-Lustig class. And now, of course, once you see such a statement, then you want to check when these two are the same. When are these the same? These are exactly the same if the local Euler obstruction is equal to the Kazan-Lustig polynomial evaluated at 1. We have Sage can calculate these Kazan-Lustig polynomials. Then you can evaluate at 1. So now, since we have access to the local Euler obstruction, we can actually check such identities. I should say that such identities have been checked. This is why I wrote these names. So Bressler, Finkelberg, and Lund actually checked directly that this characteristic cycle is irreducible. In particular, just based on his work, you can deduce what is the mother class for the Grassmannian. So you could have gotten this formula just from this work, but they do, of course, a completely different.
But technically, they use small resolution or
They use no. They analyze somehow the nearby cycle. They really use micro-order geometry. Yeah, so it's a completely different proof.
Is it known? I mean, this would be implied from EU being the local obstruction being the IC obstructable function.
That's what the statement.
Yeah, but it does it locally. I'm just saying locally for X.
Oh, this is a structural function.
Okay, I'm just doing it all local pieces. I'm just saying just EUX and ICX.
Yeah, so I don't think this is known beyond Grassmannian. So they did it in type A. So they did it in type A for Grassmannians. Then Bow and Fu, actually they did this for types A to D. What they found is that this equality holds exactly in types A and in type B. So in the seedless cases. In type C, so for the Lagrangian Grassmannian, the IC sheaf is not irreducible. In fact, if you use this formula that I was showing before, you can write down, even using our formulas, you can write down a particular characteristic cycle and how it expands in irreducible components with multiplicities. And then there was this E6 and E7 that remained, and it was so Bo and Fu use geometric analysis. It's a proof that I cannot understand. Now I'm on the record. So they use geometric analysis, and they were able to have their point of view is from the point of view of Hermitian spaces. So they can actually calculate these multiplicities in the classical types. But E6 and E7 doesn't have such a nice description.
Geometric analysis, or you mean geometric measure theory? That is right.
Maybe geometric measure theory. Okay.
That's the viewpoint of Fu of characteristics.
Yes, it's that.
I see.
Yes. That's what they use. That's
He
right.
developed them by his own language. So
That's
he has
right,
His
that's
own
right.
approach to characteristic cycles from geometric measure theory.
That's correct. That's correct. Yes, thank you. Yeah. So the E6 and E7 remained, and of course now E6 and E7 are just a finite set of situations. So what we did with Rahul after this paper, we actually I tried to do it on Maple. Maple completely failed. E6 could almost do it. So we tried to check this equality by brute force. So we know what is the Euler obstruction, we know what is the Kazan-Lustig polynomial, check if this is equal to that. And Maple kind of failed, and then Rahul wrote a beautiful code instead, which is now available on my webpage actually. You can check this equality in types E6 and E7. So using this, we actually complete the classification of Bow and Fu that says that the characteristic cycle is irreducible for each Schubert variety if and only if you have a cominuscule space of scintillate type. So in other words, it's of type A, D, or E. Okay? So you can use this. So that's what I wanted to say about connections to representation theory. It's a wide open problem what to do beyond Grassmannians. I mean, maybe this type of method can be pushed a little bit further with like more Schubert varieties, but not for everything.
I think you have answered my question. So I was wondering if one can check directly that DUX is the same as ICX without going to the basis of the indicator functions of cells. But maybe trying to relate them, these are themselves, the EUs and the ICs form bases themselves, right?
Yes,
So you're saying there's only one coefficient is 1 and all the others are 0.
Yes.
And maybe this can be checked, I don't know, with nearby cycles or something like that.
Could be.
The ICs relate to some nearby cycles. Can do some smoothing.
For me, it would be very interesting to understand this. Yeah. So let me see. So I'll try to show you some examples. So I have some slides. Can I? 5 minutes. I don't know how to start this. Oh, thank you. So so in 5 minutes,
It's probably not too strict. But
not too strict. So maybe 6.
I'm just going to share the screen.
Let's see if I find the note.
Oh, I have it.
Yeah.
I'll bring it.
I can also see it from here, so it's good. Thank you. Yeah. Okay. So let me show you. This is the beautiful picture produced by Paolo in a paper by Paolo and I. These are the CSM classes in GR25. The point I'm trying to send here is that everything is computable. You can see patterns here. So these are the expansions of the CSM classes of Schubert cells in this GR25. You can see that at the end, each of these terms here, so the terms are indexed by dimension. So the terms of degree 0 are always equal to 1, which corresponds to the fact that the Schubert cell has all characteristics equal to 1. They all start with 1, because in the CSM class, you always start with a fundamental class. And then you have some positive coefficients here. There was a theorem that there was a conjecture for a while that these are positive, and Junho actually proved this conjecture.
Is there any reason why horizontally have low concavity?
So I'll get to low concavity. I'll get there. Yeah. So just yeah. So let me get there in a moment. These are the thinking diagrams that correspond to the cominuscule spaces. So what you should see here is that I can choose, you always choose one black node, but I'm just indicating which ones can be chosen. So for example, you can choose any of the black nodes here, and this will correspond to all the Grassmannians, GR1, N, or N plus 1, GR2, N plus 1, and so on. This one gives you the Lagrangian Grassmannian. This one gives you the odd quadric. This one gives you either the even quadric or the maximal orthogonal Grassmannians, or even space, even dimensional space with a symmetric point. These are the KB plane, and this is the Poisson override. This is just to kind of like make a relation. Like we're working in all these spaces, so there is combinatorics related to all this. This is the formula that I told you. This is what we produced in the talk. It was this push forward of these line bundles. I wrote these line bundles a little bit different, but these were line bundles corresponding to the positive roots minus alpha, and you can get a little bit more. You can also get the Chern-Mother classes for the pullbacks of some Schubert varieties using the fact that we have smooth mass from a flag variety to a Grassmann. So you can get a little bit more, but using this Yakuras with the Okay, so let's see. Right, this is one example. So this is an example of the mother class of the divisor. So this says the divisor in GR24. So you see here I have 3 boxes. That means I work within dimension 3. The full Grassmannian has dimension 4. First of all, I look at the corresponding Schubert variety in the flag variety FL4. So that corresponds to 1, 3, 2. It's red bottom up and then right to left. So that's the Schubert variety. I think this was called E in my talk. So now this should be E W lambda. So when you calculate that intersection, the total Chern class of that bundle restricted to the Schubert variety, you get this type of thing. So this is the Schubert expansion inside the full flag manifold, so using this Chevalier formula. And then you're pushing forward this, and then there's lots of collapsing going on here. So some of these terms disappear, and some of these terms will add up. So at the end, you get this expansion. So this is the This is the mother class for the Schubert divisor inside the Grassmannian. Notice the 6 here. If you put the total Chern class of the Grassmannian in degree 0 has coefficient 6, because 6 is the other characteristic of the Grassmannian. This 6 is the same 6 that comes up for the full Schubert variety, for the full Grassmannian. So this suggests that the Schubert divisor is actually singular at this point, which is of course true. I'm a bit vague there, but you can see such things. You can detect singularities by looking at, for example, at degree 0. Okay, and then what else? This is an example in GR36. So you get, all coefficients are positive. You may wonder why. But you can actually prove that they are positive, for example, using the reducibility of the of the characteristic cycle of the IC shift. So you can prove that these things will always be positive, and also the positivity of the CSM classes. So if you use those things together, you will get that these coefficients will always be positive. Okay, this is an example for the Grassmannians. I'm just going to flash one for the Lagrangian. Lagrangians has like a different type of combinatorics with split partitions, which are like oriented in a different way. It's always like some poset structure there. And let me tell you about low concavity. So that's, can I get 2 minutes?
Yes, it's fine.
We are not in a rush.
You're free on Friday afternoon, come on.
We are free on Friday afternoon. Okay, so I apologize to Paolo for taking his time.
Take as much time as you want. I don't think we are in a rush.
So it's almost done. So, but I want to play this game because it was a fun game for me. So this is the game I want to play. You take any class. In this case, it's in the Grassmannian, but you can also do it in flag manifold. You take any class, expand in terms of the Schubert class. Out of this, you create a polynomial where you keep the same coefficient, but instead of writing the Schubert class, you write x to the dimension of the Schubert class. In this case, it's x to the number of boxes. So for example, here, the class that I'm considering is this mother class, okay? And then every time when I see one of these, I'm going to replace it by, this one is going to be 4 times x to the 5. This one again is 4 times x to the 5. This is again 4x to the 5. So I have 3/4 coming, contributing with x to the 5, therefore I have this 12 there. Okay? So I construct this polynomial. So we look at this polynomial. This polynomial will have no internal zeros. And then you look at the, I call this the Poincaré polynomial of the class kappa, or in this case is the Poincaré polynomial of this mother class. We say that the polynomial is unimodal if the coefficients increase up to a point and then decrease. You say that the polynomial is log concave if the coefficients satisfy the usual log concavity situation. You say a polynomial has no internal zeros if the sequence of coefficients has no internal zeros. And then the conjecture, was observed on the computer, is that the Poincaré polynomials of the mother classes and of the CSM classes, they are unimodal and they have no internal zeros. And then in type A, the Poincaré polynomials are actually also log concave. This is what the computer is telling us. To give you some examples, the log concavity seems to be only a type A thing. So for example, this is the polynomial corresponding to the mother class of the 5-dimensional quadric. This is actually smooth. So this is the total chain class of Q5. If you look at this polynomial, this is unimodal. It increases up to 26 and decreases, but it's not log concave because 11 squared is 121, and 26 times 5 is what? It's 130. So that one is not log concave. That one is a cominuscule Grassmannian of type B. So log concavity seems to be a type A, but still unimodality and no internal zeros works. The usual Poincaré polynomial of a Schubert variety is not log concave. In fact, it's not even unimodal. If you look, it's hard to, but focus on this. 27, 31, 30, 31. There's a little dip here. This one is not even unimodal. So the usual Poincaré polynomial is bad, but somehow these matter or CSM polynomials are good. Again, up to whatever my computer could do. Same thing works for CSM classes of Schubert cells in or varieties in the flag variety. And just to compare, I told you that the Poincaré polynomial of a Schubert class, of a Schubert variety, is not even unimodal. Now compare that Poincaré polynomial with the Poincaré polynomial of the CSM class. You see, it's much, much bigger. So we're talking kind of the same combinatorial data, but the coefficients are huge. This one is log concave, this one is not.
The usual contraction numbers.
Yeah, Betty numbers. These are the Betty numbers. You just look at like, yeah, this is the Betty numbers of the Schubert. So why is this the case? It could be false. So I'm not really, I guess I'm claiming that something like this happens up to whatever my computer could go to, and I tried many examples.
Up to what?
I did 8 to the 6 on the Grassmannians, so 8, 8, 8, 8, 6 times. I could do, but that was exhaustive. Like I checked every single one. Yeah, I could do maybe sporadically a little bit more, but my computer is complaining. So,
And is the boundary.
yeah. So I'll stop here. So sorry to go over time. Thank you.
Questions?
That table you showed us with the Germain classes, at least that look like top heavy, you know.
So top heaviness, that's a very good question. So I had an example that I removed. At some moment, I actually checked top heaviness. Top heaviness seems to fail for the CSM classes of Schubert cells. So I have examples, but it doesn't. It seems like for Schubert varieties, it works.
What is top heaviness?
So top heaviness is something like you have a sequence of, let's say, A1, A2, A3, A4, A5. So that's, and then the zeros after. So what you want is, you want to say something like this: A1 larger than A5, A2 larger than A4, maybe A3 is. So that's like things on the left, on the top, are like bigger than the mirror things on the other side. Now on the unimodality is not happening at the very middle, right? So but still it makes sense to check top heaviness and all that. And so that thing is, it doesn't seem to be such a good thing, at least not for the CSM classes of cells.
So you mentioned in the beginning that people were studying about the reducibility of the characteristic cycle of C. Do you know why they're interested from the work vegetation side?
I mean, it's a foundational question. So the IC sheaf, of course, is foundational in Hecke algebras, right? And then
That's clear, but still, I don't know what it would mean for them that this is a solution.
you
So
have
it
a
picks
Lagrange.
up multiplicities and representations.
No, he wants interpretations in geometric representation. So I don't know exactly. It's a very natural geometric question, right? You have a Lagrangian
Yeah.
cycle. You want to know.
I don't remember at the moment, so
Yeah.
that I was asking if you know at the moment. I don't remember what was the motivation.
Yeah. So
What does it control and representation theory information?
Further questions?
So I agree that was not fully on chapter 4.
I try to. Yeah. It's written in a slightly different way, but you can deduce it.
Deals with Gaussian invariance of Schubert over series classes of sub-schemes. So specifically
Yes. Yeah. So one needs to tweak. It's I think in like McPherson, there's this book by Brzezinski, McPherson and Borho. Yeah, Borho, Brzezinski, McPherson. Yeah, so it's this presentation. It's very close to that one.
So your vector bundles were somehow related to resolution of important objects.
Yeah. So yes, in fact, this type of technology can be pushed in that direction. I didn't. I started looking and then I got distracted.
All right. Then keep in mind that we have an afternoon discussion where we can also pick up on questions related to the docs. Maybe this has some time to grow until then. So until then, let's thank Leonardo again.
Erase this.
And